Section 12.2 talks about vectors. So, recall back from the days, a vector has both a magnitude and direction. If I pick the vector, I could label this point A, this point B. I could say this vector right here is simply AB. That's one way of expressing the vector. I could also call it vector B by putting an arrow on top, of course, on top of B. AB is more informative. It gives you where you start and where you end. Basically, it gives you direction. You could even use bold letters. That's something I'm not going to use because it's kind of hard to show when I write those. And if you map this vector on a coordinate plane, two things that you always need. Magnitude is actually the length of the vector, and direction, normally it's the angle that the vector makes with the x-axis, kind of like trig. Vector addition. If you have two vectors, if you take vector A and vector B and you add them, that's the same thing as taking B first and adding A. Now we're going to start with 2 dimensions and transfer all of this knowledge to 3 dimensions. So if you take vector A, if vector A looks like this, for example, and vector B appears like this. So what you do, if you want to start with A plus B, this vector A, you start with A, what you do, you pick B, and pretty much do you notice B moves one to the left and one up? So basically you go to the tip, basically where this vector dropped off. Think of those as moving belts, you know, to load a truck or to load a plane. You get those moving belts where you put the baggage on and it moves from wherever you drop to wherever this belt ends. Take this second vector and think of it as a belt, again moving one to the left and one up. Move one to the left, one up. So basically what you're doing, you're copying this vector. And the resultant, basically, the result of whatever you did is pretty much where did you drop off the baggage, and go in a straight path. Where do you pick it up? If this is vector A and this happened to be vector B, then A plus B is right there. And of course you could have said, well, wait a minute, why don't you go to B first, and from the tip of B run A, and guess what happens? You end up creating a parallelogram. And it doesn't matter which one you use first, the resultant is the same regardless. So the first example I have, I want to play with those vectors. Notice how these vectors work. Vector A really moves you 3 to the right and 1 up. Vector B moves you 2 back and 2 up. And vector C pretty much moves you 3 to the left. It doesn't move you up or down. Sketch the resultant of the following vectors. So to do that, you would really start with A, and what A does, A starting at the origin is going to move me 3 to the right and 1 up. There's A. So graphically, that's how we do it. And then C, what does C do? C pretty much shifts you 3 units back. So what would A plus C equal? Pretty much, where do you drop off the baggage and go in a straight path, and where would you pick it up? So that right there is actually A plus C. And if I go for B, what we do, we start with vector part B, and we go for vector B first. B starts at the origin, shifts 2 to the left, 2 up. So pretty much I drop the baggage at the origin. We always do that at the origin. And now my baggage is right there. Let me stick with the colors. There it is. Now I want vector negative A. If A moves me 3 to the right and 1 up, negative A is going to do the opposite. From this point, it's going to move me 3 to the left and 1 down. So negative A is going to move me 1, 2, 3 to the left and 1 down. And again, the resultant pretty much is, where did you drop off the baggage? Go in a straight path. Oops. And right there, that would be B minus A. Now we're going to have to do some of those graphically, and we're going to do them algebraically wise, and I'll point those out. Okay, to do part C, I'm going to have to shrink those a bit, meaning I'm going to rescale this. I tried it before, I read it twice. So let's start with negative 2A. A moves me 3 to the right, 1 to the left. Negative 2A, so I'm going to scale this 1, 2, 3, 1 down. And 1, 2, 3, 1 down. So negative 2A on the new scale looks like this. Now, C would move me 3 to the left, 1, 2, 3. Now my package is right there. And if I go for negative 2B, you know what, just so that I could fit it, because I can't, let's go plus 2B, because otherwise I'm going to have to go down, and that's going to be out of the range. 2B, what B does, moves me 2 to the left, 2 up. So 2 to the left, 2 up, and 2 to the left, 2 up. 2B, that's 1B, and that's another 2B. Remember, I rescaled this. And pretty much the resultant of all of those, where did you drop off the baggage, and where do you go pick it up? In a straight path. This would be the whole sum right there. Now we're going to talk about component-wise of vectors. Let's get those out of the way. So if I start with components, vectors are going to be a really big deal from chapter 13 and on. We're going to touch on them now, but then we're going to really fully apply them from 13 and on. If I take vector A, and that's A sub 1I plus A sub 2J. This is hopefully a review. We already know this. That's before. And the way it looked back in the days, assume, let's say that's A sub 1. Let's say that's A sub 2. So my vector pretty much looked like this. This is the notation. I use this a lot more than the traditional, but the book runs back and forth between those. Now, we're really interested in A being a sub 1I plus a sub 2j plus a sub 3k. And component-wise, we say that's a sub 1, a sub 2, a sub 3. A bit tricky to graph. The graph is not really the problem. Seeing it is the hard part. So if I assume this is a sub 1, and this is a sub 2, and this is a sub 3, my vector would really be right there. To trace it, you really have to visualize -90 degrees, 90 degrees, and 90 degrees. So, kind of hard to see. And given A to be a sub 1, a sub 2, a sub 3, and B to be B sub 1, B sub 2, B sub 3, A plus B would be a sub 1 plus B sub 1, a sub 2 plus B sub 2, a sub 3 plus B sub 3. Also, if you put a minus right there, then you really subtract the components in that specific order. If I take k and multiply it by vector A, that would be KA1, KA sub 2, and KA sub 3, where K is a scalar, kind of like a constant in real number operation. If I want a unit vector, in the direction of A, well, the length of A, which is the magnitude of A, is identical to the two dimensions, except now you have 3 components to square. A unit vector in the direction of A would be U for unit is vector A divided by its length. Now, to really show here, if you just want to represent the I component on 3 dimension, that's 1, 0, 0. The J component, that is 0, 1, 0. Okay. And the K component, that would be 0, 0, 1. Basically what I graphed right there, if those were each one. Given point A in 3 dimensions to be some x sub 1, y sub 1, z sub 1, and point B to be x sub 2, y sub 2, z sub 2. Vector AB, that's a standard vector starting at the origin, is always end minus beginning. It's x2 minus x1, y2 minus y1, and z2 minus z1. So all of these we did with 2 dimensions. Now I'm hoping to really pick that up to 3 dimensions. And let's do some examples. Find vector AB and sketch both the original and the standard vector. And we're going to do it for both 2 dimensions and 3 dimensions. So first things first, if I look at the grid, -2, 3, -1, -2, 1, 2, 3, that is vector A. That's point A, I'm sorry. And B is at 2, 1. So the vector is right there. Now, if you look at it, you'll notice this vector moves a point 2 down, 3 to the right. Well, hey, if you want to really get AB, vector AB would be 2 minus a -2 and 1 minus 3. That would be 4, -2. So if I start at the origin, this is called a standard vector. Starting at the origin, move 4 to the right and 2 down. Those two vectors are the same. You could always pick a vector. Oh, I said 3 units to the right. I made a mistake. That was 4 units to the right, if you noticed. So this is vector AB. Those two vectors are the same. As long as you maintain the magnitude and the direction of a vector, you're in good shape. You could always do that. Now, if I go for the 3D, again, a bit hard to see. Just a bit, though. So if I go for the point -2, -2, 3, 1, 2, 3, -1. That's point A. Point B is at 2, 1, and 3 up. Oops. That's B, that's A. If I look at this vector looks like this. Okay, kind of hard to see. If I find vector AB, that's actually 2 minus a -2, that's 4. 1 minus 3 is -2, and 3 minus a -1 is a 4. So if I move 1, 2, 3, 4, 2 to the left, and 4 up. Now, it's very hard to see in 3D. That's always the catch. Even though I didn't pick a very complex problem, it looks like this because you're not looking straight at it. But the components of that vector, if you really look at it, it's really the corners of this prism. Kind of hard to see, but we'll get the hang of this. Not a problem. We don't graph a lot of those. We try to see them. They're kind of hard to see, but we'll do the best. Here's one. Okay, I just changed the numbers. I tried to do that. The example I had is harder to see. I'm going to work better at making those easier to see. So, sketch A. A is 1, 3, and -3. A is right there. B is 0, 0, 4. B is simply running straight. If I take vectors A and add B to it, A plus B would be 0 plus 1, that's 1, 0 plus 3 is 3, and 4 minus 3, 4 minus 3 is 1. So if I move 1, 1, 2, 3, and I go up 1, that would be the actual resultant of this. That vector right there is A plus B. And I could see that if I go where B drops off and move straight 4 units up, 1, 2, 3, 4, you will notice that's A plus B. Again, it's kind of hard to see. When you graph it, you know what you're doing. But when you look back at it, even though you might have graphed it yourself, after a while you're like, wait a minute, what just happened? And let me get, oops. Oh, switched somehow. Find magnitude of A. Well, again, a lot of practice. Magnitude of A is simply the square root of the 1 squared plus the 3 squared plus the negative 3 squared. The magnitude of A would be the square root of 1 plus 9 plus 9. That is the square root of 19. Done deal. If I wanted to find the magnitude of A minus 2B, I need to find this first. So I'll find A minus 2B, write that as a vector. That would be A is 1, 3, negative 3, minus 2B, minus 2 times 0, 0, 4. So that's pretty much 1 minus 0, 3 minus 0, and negative 3 minus 8. That would be 1, 3, negative 11. And now that I have this is A minus 2B, I would say simply the magnitude of that is going to be the square root of 1 squared plus 3 squared plus negative 11 squared. I gotta work better at my writing. I apologize. So that would be the square root of 1 plus 9 plus 121. That is the square root of 131. There it is. We did all of this with 2 dimensions. Now I just want to expand it to 3 dimensions. Now, finding a unit vector is going to be a must, especially in chapter 16. What is a unit vector in the direction of A? Well, I already found the magnitude of A. All what I have to do is to say U is a unit vector in the direction of A. Take A divided by its magnitude. That would be 1 over square root of 19 times whatever A is. This is fine. You could also write it this way. Either way. Something I should mention. If I take, this is a note, this is a side note, something that we're going to be asked for on the long run. If I take vector A and write A as radical 19 times 1 over radical 19, 3 over radical 19, and negative 3 over radical 19. This is what I know. Since this has a length of 1, we call this direction. Of course, the direction of the vector, any multiple of the vector will maintain the direction. All of these have the same direction. But later on, when we're asked about direction, we're talking about the components. This right here is called the length. So whenever they say, take vector A and write it as its length times its direction, of course, 1, 3, negative 3 possess that same direction. All what this does, it moves right there, but it moves only with a length of 1. The direction is the same. Any multiple of that will be in the same direction. Something to keep in mind. And how about part D? Can you find me a vector in the opposite direction of A but has a length 3? Well, let's see. If this is my unit vector in the direction of A, right there, Isn't it easy to just take whatever this is, multiply it by 3? That's a vector in the same direction as A, but has a length of 3, because the length of this is 1. If I want it to be pointing in the opposite direction, just multiply it by a negative. Let me use a darker color. There we go. And that will do the trick. And that's pretty much it. So there's going to be a lot of thinking in this class. You really want to use the tools that you're given and figure those things out.